All right, so this video is a short introduction to acids and bases. So when we're trying to understand what an acid is or what a base is, it's important that we understand the H plus ion, which is simply just a hydrogen atom that has lost its electron. So it's really just a proton all by itself. It has no electrons, and because of that, it's highly reactive. An H plus is very attracted to anything that has a negative charge or negative polarity. And the molecule water has a negative dipole, or an area where it has a slightly negative area. And so the positive charge on that hydrogen is very attracted to it. And so it will actually make a molecule called hydronium, which is when the H plus, which you can see right here, is attracted to that negative area on the water, which actually is caused by lone pairs of electrons on the oxygen, if you remember the Lewis dot structure for water. And now that it's attracted to that side, we can call this hydronium, or H3O plus. Now, why do we care about hydroniums or H pluses? Well, there's two different ways to describe acids and bases. The old way is called the Arrhenius theory. It's a little outdated, it's not always accurate, but it's a very simplistic view, and so it's easy to remember. The Bronsted-Lowry theory is updated. It is accepted as the most accurate description, and it's what we tend to focus on more, although sometimes it's more difficult to understand. So looking at the Arrhenius theory, Arrhenius said that acids are chemicals that produce H plus ions when they are in aqueous solutions, aqueous aqua, water. So anything that is put into water that produces H plus ions, according to Arrhenius, would be considered an acid. Whereas a base would be chemicals that produce OH minus ions, also called hydroxide for the hydrogen and oxygen that's in that molecule, hydroxide, when it's put into water. The Bronsted-Lowry definition is a little more detailed, and it really focuses on, again, that H plus ion. So an acid would be any chemical that donates protons, or H plus ion donors. Bases then would be the chemicals that accept the protons or receive them. For example, in this equation we have ammonia, NH3, which we typically find in cleaners, plus water. And we see that the water actually will donate an H plus to the NH3. So because water is donating the H plus, in this case it's acting like an acid, and NH3 is receiving the H plus, so it's acting like a base. And then through that acid-base reaction, we've now created NH4 plus and OH minus. So in order for acid-base reactions to occur, if an H plus is going to be donated, then there has to be something there to receive it. So if acids will donate, the bases receive. Let's look at water as an example of an acid. Again, looking at that same equation, NH3 plus H2O, here the water is donating an H plus. So it is the acid. It is throwing the H plus to the receiver, which is your base. So think of it in terms of football. Your acid is your quarterback. Your base is that receiver. Now, once he catches the ball, it becomes an acid. Whoever's got that H plus ion is the acid. Okay, and whoever is ready to accept it is the base. So initially your NH3 is the base and your H2O is the acid. After the reaction, Now your NH4 plus is the acid because it's got the ball, and your OH minus is the base. It's ready to receive it back if there's a pass back. Now let's look at water as a base. Wow, that's so cool. Water can do both. Okay, so here we've got HCl plus H2O. Now your HCl is going to give away the H plus. So he's the quarterback, he's the acid. Your H2O is going to be your receiver. So H2O in this case is acting like a base. Once your ball has been passed, once the H plus has moved from your acid to the base, now the thing that was your acid is now your base because it doesn't have the H plus anymore. So in acid-base chemistry, whatever started as your acid and your base, they switch places once that H plus has been passed. Because water can do both, it's called amphoteric. It can be both an acid or a base, and it depends on the situation or the specific chemical reaction that it's involved in. We also know that acids and bases can be strong or weak, or any varying amount of strength. How can we tell? What makes something a strong acid versus a weak acid? Why is it I can put my hand in vinegar and it doesn't dissolve away even though vinegar is an acid? Or whereas I don't want to put my hand in strong hydrochloric acid because that could do harm. Why is it that some acids or bases are strong and others are weak? What is it that determines strength? So the stronger an acid or base is, the more it will break up into ions in water. And because it breaks up completely into ions, that means it's got a lot of H pluses available to react. It makes it really strong. Weak acids and bases will only partly break up in water. And because it doesn't completely break up, only a few ions will be available to react. So we call it weak. So here's an example. On the left, we have a very strong acid, hydrochloric acid. When it's put into water, it's no longer HCl combined. It breaks apart completely into individual chloride and hydrogen ions. So we can see in the diagram, we're starting off with complete molecules, then they all break apart, completely dissociating. On the right side, however, we see a weak acid, acetic acid, which is just the chemical name for vinegar. So we start off with these vinegar molecules, and when we mix it in water, only some of them break apart. Most of the molecules stay intact, so there's not a whole lot of H pluses available for reacting. So, hence we call it weak. Some common acids that you should be familiar with are hydrochloric acid, nitric acid, sulfuric acid, phosphoric acid. And here you can see they're categorized, okay? HCl is strong, HNO3 is strong, H2SO4 strong, whereas phosphoric is weak. Ascorbic acid is weak. Citric acid is weak. Carbonic acid, weak. Acetic acid, weak. Common bases: sodium hydroxide, potassium hydroxide, and calcium hydroxide are all very strong bases. They completely break apart, leaving lots of hydroxide in solution to react with those H pluses and undergo acid-base chemistry. Ammonia is a weak base. Carbonate ion is weak. Hypochlorite ion, found in bleach, is weak. Caffeine is weak. Ephedrine, also a weak base. And by weak, again, all we mean is it doesn't completely break up in water. So what are some common properties of water? Just kidding. Of acids and bases. Well, we know that water breaks up into ions, okay? And because it breaks up into ions evenly, we get H pluses and OH minuses. Acids we can define as having a higher concentration of H+, so they're on that side of the scale, and bases will have a higher concentration of hydroxide or OH-. Water is right in the middle, so we say water is neutral. It's neither acidic nor basic. We look at properties of acids specifically. Acids have a low pH. They create a sour taste in foods, so think like lemons and limes. Acids will react with bases to make water and a salt, and what's really cool about acids is they react with metals to release hydrogen gas. So if we want to know if something is an acid, all we have to do is add a little piece of metal to it and look for bubbling. How cool is that? Acids can also be dangerous, though. They're highly corrosive and can cause severe injury, so play safely. Properties of bases. Bases have a high pH, above 7. They taste bitter, so think parsley or even soap tastes bitter. Bases react with acids to make water and a salt. Should say acids, not bases, okay? It's slippery feeling, like wet soap. And again, highly corrosive and can cause severe injury, so always play safely. So what is the pH scale? It actually just measures how much hydrogen ion content there is. And it works on this weird reverse kind of numbering. So the lower your pH number, the higher your amount of H+. So that's why acids are low on the pH scale and bases are high on the pH scale. 7 is considered neutral, and that's where we would find water. So again, the pH scale is logarithmic based on powers of 10. So if we have a concentration of H+, that's 0.1 or 1 times 10 to the minus 1 molarity, then the pH would be 1. And we can see as our concentration of H+ gets smaller and smaller, our actual pH value goes up and up. And for every change on the pH scale of 1, that means something is 10 times more or less acidic. So comparing a pH of 3 to pH of 4, an acid with a pH of 3 is actually 10 times more acidic than a pH of 4. It has 10 times more H+ ions in solution. And here's just a quick graphic to show you some common everyday substances and where they fall on the whole pH scale. So again, in the middle, around 7, is where we have our neutral things like water, milk, blood. All of that falls in the neutral range. All the way down on the acidic range, stomach acid, lemon juice, vinegar. And then up on the basic range, we have ammonia and sodium hydroxide. If we want to measure pH, we can use either a pH meter or pH paper to tell us what the exact pH of a substance happens to be.